the inaugural meeting of the sort of celestial holography triangular meeting between Kings in London with Anne-Maria and Oxford with Lionel and Cambridge with me and also Anne-Maria.
She said she couldn't make it.
She couldn't make it.
Yeah.
In principle. And the idea is just to get together maybe 2 or 3 times a year just to discuss and hear about progress in celestial holography, hear about some interesting things. We got 3 talks today, which we're very excited about. And the first one is Niklas Garner, who is hot off the plane, and we'll be starting with Lionel as a postdoc, and he's going to tell us about scattering off of Twistorial line defects.
Great, thank you for the introduction. It's a great pleasure to be kicking off this hopefully very productive and interesting day on celestial holography in this wonderful Twistorial workshop that's been going on here at the Isaac Newton Institute. I wanted to tell you a bit about some research I've been doing, or well, did with Natalie Paquette in the University of Washington, Seattle. It came out last month, and that's the archive listing if you'd like to look at it. The basic aim is to try to understand aspects of celestial holography when we include line defects into our space-time. But before I get into those details, I want to draw a cartoon of what I hope to illustrate today and what sorts of things we wanted to try to understand. So the basic physics picture or cartoon behind all of this is, as you probably can imagine, we want to try to understand some scattering problems where we have some incoming particles and some outgoing particles. And the basic aim is to try to understand scattering amplitudes, which all of you know and love. And the starting point for this problem, at least for me, I'm sure many of you all have your own starting points, but the starting point for me came with some work done by Natalie together with Kevin Costello back in 22, that roughly says the following. If you start with holomorphic field theory, that'll denote by T, and place it on Twistor space, which I'm sure you all know and love, but you can think of it as the total space of rank 2 vector bundle over P1. Then there exists vertex algebra, or chiral algebra, depending on what flavor you like. And a 4-dimensional quantum field theory, or classical field theory, that I'll denote by T, but with a subscript 4D to differentiate it from T, such that, and this is a field theory on R4, this being the Twistor space of R4, such that, well, first of all, generators of this vertex algebra, I forgot to give it a name, it's going to be V, are in 1-to-1 correspondence with negative dimension conformal primary states. In the 4-dimensional theory. So that's negative scaling dimension states. The second bit that they were able to establish was that conformal blocks of V, and you might be used to situations like WZW theories or current algebras where there's sort of one conformal block on the 2-sphere. In this context, you have an infinite number uncountably infinite number of conformal blocks. And in the four-dimensional picture, these correspond to local operators.
Uncountably infinite because you choose the point.
Pardon?
Uncountably infinite because you choose the point.
Exactly, yeah. So conformal blocks of our chiral algebra V are in one-to-one correspondence with local operators in our four-dimensional theory. And then the juicy bit that ties back to this cartoon I drew is that correlation functions in such a conformal block and I'll just denote it schematically by that, where this will be the corresponding four-dimensional operator, O. These correlation functions on the chiral algebra side compute form factors in the four-dimensional theory. And so this cartoon needs to be adjusted ever so slightly. Form factors you should think of as scattering in the presence of local operators. So I imagine computing some scattering process, but I don't scatter in just empty space. I have some local observable that I envision in this cartoon as being some thing I can do to my system at some point in space at a fixed time. So I imagine doing scattering processes where, in addition to scattering states, I have them scattering off of some local operator.
So that's not Acme, that's a subset of...
No, that's Acme, like the cartoon toys, and yeah, that's meant to be just a joke. It wasn't.
Oh, sorry. That
It's
wasn't
like
a subset of.
No. That's Acme.
I'm sorry. Yeah. Okay.
Sorry, I can't write diagonally very well. So this story developed by Natalie and Kevin establishes this framework for computing form factors in a purely algebraic fashion. So the upshot of this picture that they were able to establish, that scattering in this four-dimensional theory is highly constrained. And in fact, it turns into a problem in algebra. And is highly constrained by the symmetries thought of as this chiral algebra. You might be familiar with these as like holomorphic symmetries of a two-dimensional conformal field theory. In the same sense here, this chiral algebra V is some infinite dimensional symmetry algebra of this four-dimensional theory. And of course, as you probably well know, these are precisely the celestial symmetries of our four-dimensional theory. And of course, if you've computed anything in scattering, you know that you often can't have things this simple. And of course, not all theories can be written in this fashion. And so the types of theories you get from doing this reduction of a holomorphic field theory on Twistor space are dubbed Twistorial. So the types of problems we're interested in are understanding scattering in twistorial field theories in four dimensions, and it's scattering in the presence of local operators. And this was the program established by Natalie and Kevin using this chiral algebra bootstrap of sorts. My work with Natalie enriches this ever so slightly by not only having my Acme laser blasting my scattering problem, but I also imagine throwing some heavy particle into the mix as well. So not only am I shooting my scattering experiment with a laser, I'm also imagining I have some heavy quark or bowling ball or something in the middle of my scattering experiment that my particles can scatter off of. So in this cartoon, we not only are interested in form factors, but scattering in the presence of local and line operators. So in words, our work extends this work of Natalie and Kevin to include scattering in the presence of line defects. In the presence of line defects. And these sorts of problems show up all over the place. The famous Kondo problem is studying scattering of electrons off of some magnetic impurity in your system. We also have situations where we scatter off the presence of some heavy quark, and that corresponds to inserting some Wilson line. And so in some sense, this is meant to be some algebraic framework for studying these types of scattering problems, where we have some heavy particle in the middle of our system. Perhaps we're blasting it with a laser during the scattering process. And at the end of the day, we're going to be able to compute these scattering amplitudes or form factors purely algebraically. Of course, this relies heavily on the fact that we're working with Twistorial field theories, and not all line defects are created equal in these theories, and so that's where these Twistorial line defects come in. Namely, these are going to be line defects that play well with this correspondence between 6 dimensions and 4 dimensions.
Now, this is what you're considering, but if I wanted to take your local operator and just integrate it along the line, would that fit into the framework easily?
If you had a Twistorial uplift of such an integral, yeah, I think it should.
I mean, of course, what I really want is take your local operator and integrate it over the whole space-time, and then it's a vertex in a non-celestial theory.
Right. I would imagine that sort of being a version of integrating these correlation functions over the insertion point of that local operator. That's what we're going to end up doing at the end of the day. I imagine that you could try integrating those things over lines rather than all of space-time, and maybe you could reproduce some of these same things. I'm not sure whether you'll be able to do those things purely algebraically, because integrals can be hard, but in principle, it seems kosher.
And when you say the generators of the negative dimensional formal primary states in 4D theory, you're not talking about scattering states there, are you?
Yeah. So those are...
So these are just the asymptotic states that somebody doing amplitudes would be talking about.
Right, exactly. So there are often really nice bases of this chiral algebra where you do some generating function. You have some infinite linear combination of these sort of basic states, and those will be genuine scattering states. So like momentum eigenstates, for example, will fit into that class where you consider some formal sum, or maybe not formal, but some infinite sum of these formal primary states that sort of become genuine momentum eigenstates, for example.
And then when you say conformal block, that's something that these generators know how to act on.
So for me, a conformal block is the following. You can imagine computing some correlation function where you have some insertion of your local operators in this vertex algebra V, and they're placed somewhere on, for example, the sphere, and you can ask how constrained is that correlation function purely by the symmetries of V. So if I ask that this correlation function has the appropriate singularities as I bring my points together, how constrained is that correlation function? And the basic statement is that it's not necessarily unique and often isn't, and in fact this is highly non-unique, And the non-uniqueness is precisely labeled by a choice of local operator in 4 dimensions.
I see. And that local operator could be any old sort of trace of curvature to the 23 or something.
Right, exactly.
Yeah.
Yeah. So for me, correlation or conformal blocks is some measure of how non-unique a correlation function is using only symmetries alone. And the statement here is that it is highly, highly, highly non-unique, and the non-uniqueness is labeled by local operators in 4 dimensions.
The notation is suggested the thing is a sort of vacuum state in the 2D theory.
Maybe not a vacuum state, but perhaps like a dual state. Yeah.
Okay. And usually in 2D, there's 2D CFTs is a state operator correspondence, but also there is a local operator in the 2D theory. And you're not claiming that here.
No, not exactly. No, it's not going to be.
State operator correspondence. Is it because it's chiral?
I might say that the I would say that maybe it's not quite a state in 2 dimensions. I might have even said it's a state in a 3-dimensional sort of bulk theory in some sense. I'd be happy to elaborate on that afterwards if you'd like, but it's not literally a state. I think the notation should be like perhaps I have my vacuum state, I imagine being sort of the vacuum state of V, and I have some currents that are acting on that state, and I want to get a correlation function of these J's. And so the notation is really meant to sort of be evocative of like, what's my bra? To like define the correlation function, if you will. So it's not quite
standard state things in
right.
Field theory, in particular in 2D CFTs, let's say there's a local operator in that theory corresponding to.
Right.
You're not saying that here.
No. It's just meant to be evocative of this sort of, how do I go from some general state in my theory, which is some collection of local operators acting on a vacuum state, to get a correlation function out of it. So it's like, what is the thing that I put right here to get the correlation function?
Some choice of homomorphism from products of V to complex numbers.
Right.
It's clearly a choice, but somehow the choice is not simply labeled by the states in the operators in the 2D theory.
Right.
Operators in the 4D theory. I know that's true, and I see how it works. I just don't know.
Yeah, perhaps a better notation would be like something like that, rather than a bra. I don't know. It's meant to be evocative more than anything. It's not like a state necessarily. I mean, there is a sense in which it is a state, but that's not quite something I'll discuss here. Yeah?
Can't you interpret it as like a marginal deformation of your CFT? You're pulling down one copy of it because of conformal correlation theory, some kind of conservation law. To pull down one copy of this, you're not doing a copy of that. Isn't that the picture?
I think that you could probably make that picture work, yeah. It's not necessarily the perspective I typically take, but you could probably make it work, yes. Any other questions? Okay, I probably won't be able to describe that here, but one nice application of this framework that we were able to develop is to reproduce some nice scattering amplitudes found by Lionel Latoul, Giuseppe Bagna, and Tim Adomo for a particular choice of theory T and a twistorial line defect known as the self-dual dion. And that's going to be more or less the running example, but I won't get quite to correlation functions, I think. But with that in mind, let me just tell you some of the properties that Natalie and Kevin described in that running example. So this first section, if you will, is going to be our running example. Which is going to be holomorphic BF theory. So just to establish some notation I probably won't use. I'll have, oh, I can't use green. I'll have some homogeneous coordinates on my P1 that I'll call lambda sub alpha. And then we'll have some fiber coordinates, mu alpha dot. And these are all homogeneity 1. And the theory we're interested in has an action of the following form. We have a field B that is a 1 form valued in O minus 3, or a 0, 1 form, not an O minus 4, sorry, together with the curvature of a holomorphic gauge field, A, and the action takes this form. The equations of motion, of course, say that this curvature vanishes so that A is a connection on a holomorphic bundle. I guess I'll also fix a gauge group G. I'm going to be lazy and consider this a complex group, but really should take some real form in 4 dimensions, but we're doing perturbation theory, it doesn't really matter too much. And the other equation of motion for B says that it's a holomorphic section. I need a trace. It's a holomorphic section of this holomorphic G bundle. And so Ward tells us that the corresponding 4-dimensional theory, T4D in this case, is simply self-dual gauge theory. Perhaps you'll write a G here. And then one of the key properties that Natalie and Kevin were able to establish is that these celestial symmetries that we were talking about before, this V, one way to get at them they're the same thing as gauge transformations. Away from lambda 1 equals 0 and lambda 2 equals 0. So of course these are homogeneous coordinates on P1. These 2 points, lambda 1 equals 0 and lambda 2 equals 0, correspond to the north and south pole of Twistor space, or of the Twistor P1. So let's see what that looks like. Well, what are gauge transformations? And I'll do some sort of BRST type formulation. So gauge transformations are going to be encoded in a BRST differential. I won't use the full BV formalism. I'll try to keep things down to earth for the most part. The gauge transformations of my connection, my gauge field, are the usual ones. I can shift it by the covariant derivative of some ghost field C, some BRST ghost field. The gauge transformations of B, they come in 2 forms. I can act with gauge transformations, which, because B is some adjoint valued thing, just acts by the commutator with the same gauge parameter. But I also have the freedom to shift B by the covariant derivative of something that I'll call little b, of that form. So there's 2 types of gauge transformations. There's the C type and the B type. And these gauge parameters also transform under gauge transformations. C transforms to the commutator, or perhaps you should say anti-commutator. I'm going to use this notation where this is an anti-commutator if the 2 things are fermionic, or a commutator if one of them is bosonic. And the B-type gauge transformation just transforms like that. And if you're familiar with this, you should think of this thing right here as the Chevalley-Eilenberg complex for gauge transformations. And so unpacking this a little bit, we'll have two types of generators for our celestial algebra. We're going to have one I'll call J sub A with two types of parameters, R and K. And these will correspond to when my ghost field looks like this, Z to the K, B1 dot to the R1, B2 dot to the R2, TA, where this is going to be some basis of the Lie algebra of G. V alpha dot is going to be equal to mu alpha dot over, say, lambda 1. And Z is the local affine coordinate on P1, given by the ratio of lambda 2 over lambda 1. And all of these parameters are integers, with R1 and R2 being non-negative. So this will be one family of generators. And then the second family, I'll call J tilde, where B is that same form. And then this Chevalley-Eilenberg complex translates to the following commutators of these. Oh, I also have to say R is just the tuple R1, R2. So this will be some giant affine-like algebra with the structure constants of my Lie algebra showing up. I add this pair of tuples, and then I sum the Z modes. And then there's a similar one for commutator
You mean alpha?
Yes, thank you. And then the commutator of two J tildes is going to be equal to 0. Just for those who like pattern matching, this bracket is encoded in this term in the differential, and this bracket is encoded in this term of the differential. Two C's correspond to two J's. B and a C correspond to two J tildes. The right-hand sides, this corresponds to this guy here, and this guy corresponds to that guy there. So the fact that C transforms into the bracket of two C's is precisely a statement that two J's bracket to a J, and the fact that B transforms to a bracket of C and B says a J and a J tilde give me a J tilde. The fact that I don't have a B commutator anywhere says that J tilde and J tilde have a trivial bracket with one another.
When you say J left right arrow C, what you mean is the J's are the modes of C as a field?
No, I would say that.
Okay.
Yeah. So I will have some gauge transformation when C takes this value, and that will correspond to some symmetry. So for each sort of mode of C, I have a corresponding symmetry. When C takes this form, then the corresponding gauge transformation will be denoted by that.
Yeah, so these are the charges then that we're familiar with.
Right. I was going to.
Yeah. Okay, sorry. I see what you're saying now. So the actual gauge transformation is then generated by a current, and the current will be multiplied by that mode.
Right.
And so on and so on. Okay, so these are currents as the notation would suggest.
Right. And the next thing I was going to do is exactly write those currents.
Okay.
The Z mode can all be summed together, and this can be rewritten as a nice operator product of a form that you might be more familiar with. I imagine having some formal sum over the Z's or over K, and this bracket on the top line can be rewritten as this operator product expansion being a simple first order pole. Like this.
You see, you've written C as a holomorphic function, and perhaps you could have done it sort of with some anti-holomorphic dependence too. Would that be allowed, or would that sort of just...
Sorry. This should be gauge transformations away from 0, preserving the vacuum. A equals B equals 0. So had there been an anti-holomorphic component, then that would change vacuum. Thank you for pointing that out.
Secretly, of course, C seems to have got poles, and so that D bar would... Anyway, I know what's going on.
But these are away from one of the north and south pole, so Z inverse is a holomorphic function.
Okay.
Yeah.
So you're just saying that away from lambda, away from the poles.
Right.
But in some sense, Lorentz invariance is broken. Is that why you want?
I suppose so, because you're saying rotating P1, which is one part of the Lorentz group, will rotate the north and south poles.
Yeah.
Yeah, that's not necessarily a problem, because if you, for example, inserted some operator on P1 at, say, point Z, that would also break invariance because you're then rotating the insertion point. Everything is Lorentz covariant, though. And so at the end of the day, when you look at correlation functions, everything will be Lorentz invariant. But the Lorentz invariance is in principle already broken by inserting my local operator on some point Z.
Seems to me that it's screaming for a non-projective version.
Non-projective? I mean, in some sense, I've gone to affine coordinates, if you'd like. Do you mean on Twistor space?
Where you replace the P1 by C2 minus the origin.
I'm not quite sure what you mean, but I'd be happy to talk more about it.
But this is a usual...
I mentioned this in my talk.
Yeah.
Right. And then the only thing I wanted to point out, or the last thing I wanted to point out in this first section, is that these are precisely the types of celestial current algebras that you might be familiar with from, say, Alfredo's work on celestial symmetries, or much earlier work as well. Okay, so that was just the vanilla stuff that Natalie and Kevin did, showing that these celestial symmetries have a nice realization as gauge transformations. There's also a much deeper, elegant formulation of these things that Natalie alluded to last week, where you can realize these symmetries via a notion called Cazul duality. It's a bit to unpack, so I won't try to do it here, but feel free to look at the paper of Natalie and Kevin or the archive listing I mentioned up there. Instead, I wanted to go to the celestial symmetry algebras that you get once we introduce line defects. And so in order to do that, I wanted to sketch a little bit of what Twistor spaces look like when we have these defects. And I'm going to imagine my line defect is placed at some point, let's call it x1 equals x2 equals x3 equals 0. So the origin in R3 and extended along x4. And so the main subtlety that you run into is that fields on the complement of this line are double valued. Upon complexification. Essentially because we have this nice variable r, which is the square root of this distance to the line. And once we complexify space-time, this will no longer be a single valued function. If we take some transit where we bring our x's around one loop, we find that this expression can pick up a minus sign. And so what we need to do is to work on the Twistor space of the double cover of R4 minus a line. And thankfully, Twistorologists from your told us how to do this. The first thing to note is that points on Twistor space over the complexification of this line satisfy a nice relation. They have the following expression equal to 0, where this matrix takes a particularly simple form. It's just some identity like matrix. And I'm going to call this expression here some calligraphic Q. And Bailey, back in '85.
I should think of T as tangent to 1.
Right. Yes, exactly. Yeah. So this is that's exactly right. If I were to consider a different line L, that's not necessarily along the x4 axis, that would change this. But I'll just stick with this one. And so Bailey says that the Twistor space of this double cover, which I'll call PT sub Q, is perhaps something at first sight a little bit scary. It's a non-Hausdorff complex manifold where I take two copies of Twistor space, this ordinary Twistor space. I'll call it PT plus and PT minus. And then glue them across the locus where Q is non-zero. So this is some non-Hausdorff space. I'm taking two copies of Twistor space and gluing them over some closed set. Sorry, over some open set. And if you've played with algebraic geometry, you might think this looks like the plane with a doubled origin. That's sort of the same kind of model that you should have in mind when looking at this Twistor space. But this non-Hausdorff space is the Twistor space for our double cover. So at the end of the day, this is the manifold, sorry, not manifold, this non-Hausdorff space is what we'll be trying to study. And there's some other things you can look at. There's Bailey and Singer. A nice paper by the two of them, but also a nice compendium. The Further Advances in Twistor Theory, everyone's favorite. I've spent lots of time with this guy, volume 1. And chapter 6 is dedicated exclusively to studying twistorial uplifts of these sources. And this is where I learned about this non-Hausdorff twistor space. So if we're interested in studying scattering in the presence of line defects in our twistorial theory T4D, the main game will be to take our 6-dimensional holomorphic theory T and place it on that non-Hausdorff space PTQ. So let's go back to our running example of holomorphic BF theory and just sketch what it looks like. Just a reminder, the equations of motion say that we have some holomorphic G bundle on our manifold together with an adjoint valued holomorphic section B. So let's digest that a little bit. So what's a holomorphic G bundle on this twistor space? Well, this is going to be identified with 2 holomorphic G bundles. On twistor space, thought of as the 2 holomorphic G bundles on PT plus and minus. And we want them to be isomorphic to one another on the open set where Q is not equal to 0. So let's digest what that means in terms of our fields. We imagine having, in some sense, 2 copies of our fields. I'll put pluses and minuses corresponding to which copy of twistor space they live on. And we have 2 holomorphic G bundles. So that just says this anti-holomorphic curvature vanishes for both of our fields, A plus and minus. And we also have to impose or introduce an isomorphism between them. And I'll call this isomorphism curly G. And its equations of motion say that the restriction of my of my gauge field A and of my gauge field A plus and minus, sorry, satisfy this equation. And if you act with G inverse, this is equivalent to saying that A plus is equal to the gauge transformation of A minus with respect to G. So these 2 gauge bundles are related by a gauge transformation over Q not equal to 0. This vertical slash indicates that I'm restricting it to this open set. There should be one there. And so this is in principle some invertible map from Q not equal to 0 to my gauge group G. And then
With the curly G, I can use the general gauge transmission to add a single option.
right, exactly, yeah. So for example, it could depend on Q inverse and things like that. Q isn't invertible except when you look at the locus, it's not 0. Okay, we can do the same thing for our B field. We're gonna have B plus and B minus. It's kind of just copy and pasting that formula and throwing on some pluses and minuses. And we want them to agree in some sense over this overlap so that we can have some holomorphic section over everything. So at first glance, it might look something like this. I take the restriction of B plus and I subtract off the gauge transformation of B minus, the restriction of B minus, sorry. And you might want to set this equal to 0, but this turns out to be a bit too restrictive. And instead, what you should do is say that it should be the variation of a field I'll call B0 that sort of lives away from Q equals 0. So in addition to having A plus and A minus, B plus and B minus, the new fields we have to introduce to work over this non-Hausdorff twistor space are this field G and B0. And just to do some matching of things, A is a one form, it's a connection, one form. A plus and A minus, that's both true. So for this equation to make sense, G is like a function. Of course, it's our gauge transformation. Same thing here, B is going to be a 0, B0 is a 0 form, B plus and B minus are both one forms. And so G and B are both sort of functions, if you will. Right, yeah, so this superscript is meant to denote the gauge transformation of that quantity, and of course the gauge transformation of these things are given as above. So this is really conjugate G, and this is conjugate A and shift by G inverse del bar G, which is how gauge transformations act on an adjoint section and a connection one form. Ooh, that doesn't work. Okay, so this is some sort of non-perturbative thing totally in terms of holomorphic G bundles and all that. What we're going to want to do at the end of the day is to fix some background and work perturbatively around that background. So we want to do perturbation theory in the presence of some fixed holomorphic G bundle on this non-Hausdorff twistor space. So I'm going to imagine that my calligraphic G is actually some fixed background I'll call G0. And we're going to allow or consider some small variation away from that. That's parameterized by a new field I'll call A0. And so when we do this, we can look at these equations of motion for G and find the following equations of motion for A0. And we also have to rewrite the equations of motion for B0 because it has a G in there. Minus. So the equations of motion we're going to be interested in are curvature of A plus and minus vanishes, covariant derivative of B plus minus vanishes, and then these seemingly god-awful equations for B0 and A0. And of course we're going to be interested in looking at gauge transformations away from the poles of our twistor P1. So let me now write out my gauge transformations. For A plus and minus, B plus and minus is going to be the exact same as what I have up there. So let me write out the gauge transformations of A0 and B0. They go as follows. C plus A0 So we act on the left of A0 with C plus and on the right with C minus gauge transformation, or conjugated. And then we also have the ghosts themselves showing up. And gauge transformations of B0 look like this. And so now we can try to stare at this for a while and come up with something up there. But what we really want to do, or what I want to try to end with, is getting some specific example out of the way, just to give you something to chew on. And so now I'll choose a background, a particular choice of G0 that's going to be able to reproduce the self-dual Dion computations of Lionel and Atul and friends. So in order to do this, I need to tell you about a specific bundle. That'll reproduce the self-dual Dion. And this thing is known as the Coulomb bundle. And it was discovered, from what I understand, based off this further advances in Twistor's theory, by Roger Penrose and George. And I'll just write it schematically. The self-dual Dion can be realized by taking our gauge transformation G0 to be the inverse of Q. I think they might have done the inverse of this line bundle, but okay. So we can realize the self-dual Dion configuration in 4 dimensions by looking at the 6-dimensional bundle on this non-Hausdorff twistor space, where I take my gauge transformation G0 to be Q inverse. And I can explain a little bit in more detail what that looks like. And we can take this abelian field configuration and embed it into G-gauge theory in the usual way by taking C star or U1 and embedding it inside our favorite maximal torus of our gauge group G. And you can also think of this as choosing some element T0 in the Lie algebra of our gauge group that's diagonalizable with integer eigenvalues. So it's semi-simple. It's a semi-simple element of our Lie algebra, and it's got integer eigenvalues, also called a co-character, T. Kind of want to keep that. So now we can turn the same kind of crank that we did before. I told you about gauge transformations of my fields. So that was the details I buried in saying this statement here. Really what you have to do is to choose holomorphic G bundles on the 2 copies of Twistor space. One way that it's described in this further advances is to take one of the gauge bundles to be the trivial one, and the other one to be O-2. And then this is our isomorphism of those 2 bundles away from Q equals 0. The one that we do in our paper with Natalie is to actually take O plus and minus 1 on the 2 copies, and then this is the same story as the one in further advances, but just tensor with O minus 1, or O1, whichever it is. So yeah, I buried that in there, but that's a good point. Thank you for mentioning it. G is just a function. It's just like a usual gauge transformation. So what do we do? Well, we have this Chevalley-Eilenberg complex for gauge transformations, this C and B, plus and minus, that show up in these gauge transformations that I wrote up there. And we can turn the same kind of crank of figure out what the corresponding gauge Lie algebras are. But one thing I want to mention is that we shouldn't just look at C plus and minus, B plus minus. We should also include A0 and B0 in that discussion. And I don't have time to explain that, so let me save it for afterwards if you're interested. But at the end of the day, we've got some Chevalley-Eilenberg complex that's 2 copies of that one, together with these transformations as well. And so I haven't been moving this forward because I knew I wouldn't be able to write this in time, so I prepared it ahead like any good chef, or television chef, I guess. And so what does the gauge Lie algebra look like? Well, I've got 2 copies of that thing I have up in the middle board. That's what this first line says. I now have a plus and a minus. I'll explain what this superscript M is in a second, but this is just 2 copies of that Lie algebra I had up there. And let me write out what this this superscript thing is. The first thing to say is that J0 is just the same thing as J. Same thing with the tilde versions. And the higher values of M are determined as follows. Let me write it this way. So it's in terms of the lower values of M. It's just some linear combination of my states, and this will turn out to be a convenient basis. In some sense, it comes from the fact that if I work in these same homogeneous coordinates and look at Q, which is this calligraphic Q divided by lambda 1, this is V1 dot plus Z V2 dot. And so you can see that this calligraphic M, this superscript M operators corresponds to just a nice reparametrization, if you will. So we have Z to the K, Q to the M, V1 dot to the R1, V2 dot to the R2, TA. And this relation here just reflects the fact that Q is actually determined by Z, B1, and B2. In these expressions, M and N are both non-negative, corresponding to the fact that they live on all of Twistor space. In these, I have a new set of operators, psi and psi tilde. Psi will correspond to A0, and psi tilde to B0, B0, and the superscripts and so on correspond to the same sorts of things. But here, because these these fields A and B, 0, live over Q not equal to 0, these operators are allowed to have M and N an arbitrary integer. They can have negative values of M and N. And then the last thing I want to mention is that this isn't just a Lie algebra. If you've played with Chevalley-Eilenberg complexes before, these quadratic terms correspond to brackets, as I was sketching up there, but it also has linear terms. And when you look at Chevalley-Eilenberg complexes of this form, these linear terms precisely correspond to having a differential as well as brackets. So really, what we end up finding is that the celestial symmetry algebra around a self-dual dion isn't just a Lie algebra, but it's a Lie algebra equipped with a differential. And I didn't have time to write the differential before, but I'm happy to write it if anyone is interested. The punchline is that this differential is what helps us do this gluing away from Q equals 0. In some sense, C plus and C minus have to match away from Q not equal to 0, and this differential does that cohomologically. Cool, so I'm now 2 minutes over time, so let me just end with some extra bits.
Is it fair to say that naively you have a doubling of degrees of freedom, but the differential, the cohomology of this differential brings it back?
It not only brings it back, but also reduces it. So what you end up finding is that cohomology of this differential in degree 0, so just restricting to the j's and j tildes, is actually smaller than the sort of ordinary celestial algebra.
So they're not the same amount of soft gluon states in the celestial dion?
I mean, it's a countable infinite number, but yeah, it's strictly a subalgebra. In some sense, this is like the subalgebra preserving the dion, if you will. That's the way that I would think about it. But the form of the brackets is exactly the same. So in some sense, the symmetries are morally the same as those before turning on the dion. You just lose some of them because they don't all preserve the dion.
So like the algebra of large case transformations, in some sense, that preserve the background.
Right, exactly, yeah. That's exactly how you should think about it. Okay, so the punchlines that I wanted to end with are that many of the familiar features from the original story continue in this story of sources. For example, if you take this Lie algebra, or DG Lie algebra, and start asking about conformal blocks and correlation functions in those conformal blocks, you can reproduce these scattering amplitudes of Lionel and Atul and friends. That's something that we do very explicitly in our paper, although it's beyond my time. One thing that I will mention as sort of an asterisk is that we weren't able to establish a correspondence between conformal blocks of this DG celestial symmetry algebra and local operators, although we expect it to be true as well.
But you have the trace B squared block.
Yeah, so we are able to write down a block, but the question is, are all blocks corresponding to local operators? We can provide a lot of evidence that the block we look at is precisely the trace B squared block, assuming that identification makes sense. And we have a lot of consistency checks of why that is an appropriate name for the block we found or worked with. But a more general story like this result of Natalie and Kevin's that has an isomorphism between conformal blocks and local operators is not there yet. But it seems totally reasonable in my opinion. And then, what?
What's the abstraction?
So the way that Natalie and Kevin show this isomorphism is by doing a reduction down to a three-dimensional holomorphic topological theory, and then using some identification between local operators in 4-dimension and states in this three-dimensional theory, which are in turn identified with the conformal blocks. So there's some triangle, if you will, of states in this three-dimensional theory, local operators in 4 dimensions, and conformal blocks. The problem for us was we weren't able to do that reduction in the same way. In some sense, the 3-sphere is a little bit more complicated when you have this line operator inserted. You pierce this 3-sphere at the north and south pole, and that sort of makes the computation a lot harder. But in principle, I would imagine that there is a 3-dimensional holomorphic topological theory, exactly as Natalie and Kevin found, that admits a boundary chiral algebra with this Lie algebra of modes and the differential I didn't write down. And states of that 3-dimensional theory would then be identified with local operators in 4 dimensions. But we weren't able to establish that isomorphism. It's just a matter of having willpower to do it. And then the last thing I wanted to mention was that there's a whole slew of generalizations beyond this self-dual dion computation we did. Even within the self-dual dion world, you could try attacking things beyond gluon scattering off of self-dual dions. And one thing that I think would be really interesting, a cute little project, would be trying to understand fermion monopole scattering by doing a sort of self-dual version of QED and then taking this exact same construction and trying to reproduce some known properties of fermion monopole scattering. It'd be a fun problem for the students in the audience.
I suspect Alfred Henry might have been doing that.
Yeah, great. And then the last thing I'll mention is that gravity is also something that should be applicable. We saw in Lionel's talk the twistorial uplift of gravity, and you could imagine doing scattering of self-dual black holes in the same sort of fashion, given an appropriate background in this theory of holomorphic BF theory, Poisson BF theory on this PTQ, and then turning the same kind of crank. So there's a whole slew of examples that one can pursue with these techniques. We just gave a sampler for people to work from. And with that, I'll end.
I'm going to totally abuse my position because I don't want many questions because we're in danger of running out of lunch. So I'm going to ask the only question. So,
I would like to ask.
oh, actually, no, okay. George, please.
We'll make some statements. One is that there's a remarkable fact that the analog in gravity, self-dual gravity of the Coulomb, does not have a Hausdorff.
Ah. Yeah, it's not. That's right. It's not. It is Hausdorff.
Yeah, it was. I was amazed to discover that.
Wow.
Okay, you're right. Yeah.
Secondly, this is absolutely amazing stuff. Sorry, I have a question. I forgot what it was. Oh yeah. You have your x1, x2, x3 is 0.
Right.
And you mentioned that you could change your t if you wanted to.
Yes.
But if you think of it from the conformal point of view, there are different kinds of well lines. In particular, the one you have is one that goes through I plus and I0. But you could have what's called a uniformly accelerating well line, which actually pierces scri plus and scri minus. And I was wondering what the difference would be. Of course, then the real question is what happens when you start putting these well lines together and having them collide?
That is, so for the first question, what I can say is that it probably doesn't change the celestial chiral algebra all that much. Or at least that would be my guess. We were actually working in Euclidean signatures, so, okay. But it's signature agnostic, and I would imagine that you would get the same celestial chiral algebra in different signatures. And the choice of world line is in some sense buried in what this Q is defined to be. So if you were to rotate that world line to something else, then that would just change what Q is, but the form of the Lie algebra wouldn't really change all that much. If you go beyond straight lines, I've got no idea. But I would imagine, hope, that you would have a lot of similar techniques available in that setting as well. This is some sort of like local picture, if you will. And then colliding world lines, oh boy, that would be really cool. I don't have anything to say about it other than that sounds really cool.
So, just to take it back to a very physics point of view, so the top two, well, the original algebra you wrote down over there, I could think of as just very soft gluons radiating off an external gluon in some process, as either listed. Listed, I guess, is the one radiating. Can I think of the new generators as the same thing, but where my soft gluon is radiating off this defect?
I don't think it necessarily needs to radiate off of the defect, but I think you should still think of these J's and J tildes as corresponding to soft gluons.
It does look like they're radiating off the defect. On the left, sorry, up there I've got two gluons coming together to form the gluon on the right hand side, or gluon of two helicity. It looks like with this J and psi, I've got a gluon coming together with my defect to form still a gluon. Oh, sorry, still
Well, there's no gluons on this right hand side.
The defect remains, right?
Right. Yeah, I don't really have a physical interpretation for what the sort of non-zero ghost number degrees of freedom look like. At the end of the day, if we wanted to reproduce the results of a tool in Lionel, we just focused on the degree 0 generators, which we think of as gluons in the usual sense. But I think better understanding these other components of the celestial symmetries is a really important thing to do. Morally, they're the things that make sure that you preserve the dion configuration. You don't want your large gauge transformations to change the background in some sense. But what the Lie algebra part is doing, the stuff beyond the differential, I really don't have a good understanding of. But it does sort of feel like you have a gluon scattering into the defect in some sense. Just sort of exactly as you suggest, you have gluon defect goes to defect kind of interaction. But I don't really have a strong physical explanation for what this Lie algebra is really doing.
Okay, let's thank you again.